Hi everybody, this is Dr. Bricker here with an introduction to our next lab, force and direction on a current carrying wire in a magnetic field P&W. Let's take a look at the lab. So there's 4 parts to the lab. The first few deal with the direction of the force on a current carrying wire. And then the last part deals with using the Lorentz force law for a wire to calculate the actual length of the wire. Let's kind of take a look at this. So learning objectives. When current flows through a wire that is immersed in a magnetic field, a force is exerted on the wire. So this goes back to what we saw earlier in the current chapter. Moving charges in a magnetic field experience a force. So if you have a wire and current is flowing, current really is just the motion of charged particles, electrons. So if charged particles are moving in an electric field, they're going to experience a force. It just so happens that the moving charges are in a wire, so the wire is going to experience a force. That's what this whole concept is about. Okay, so the first part again deals with figuring out the direction of the force. Okay, so here you see the equation for the figure out how much the force is. So the force is equal to I, which is the current. L is the length of the wire that's in the magnetic field. B is the magnetic field strength. And then the sine of theta here, that's the angle between the current and the magnetic field. So in this lab, the angle is actually 90 degrees, so the sine of 90 is 1, so the sine of theta part goes away, as it says here. Let me scroll down a little bit. So here's this right-hand rule that we have. Now this is somewhat different the way that they're doing it here. It's the same idea. You've got to line these things up. So you put your pointer finger in the direction of the current. The finger next to it is the direction of the magnetic field, and then your thumb is the direction of the force. So those are all perpendicular to each other. If you can see it, I've actually written I on my pointer finger, B on the magnetic field, and then F on my thumb. That's the direction of the force. So these are all perpendicular to each other. The force is perpendicular to I is perpendicular to B is perpendicular to the force. Now in that textbook, they still have a right-hand rule. They just called things differently. So it's the same idea. These things are always perpendicular to each other. The force is perpendicular to the plane made by I and B. I and B don't necessarily have to be completely perpendicular to each other, but the force is perpendicular to the plane made by I and B. So the first section or so, first 2 sections, I believe, you've got to line these things up. So here's I again, here is B, and then here's the force. Okay, so it's just a matter of lining these things together. Let me scroll down a little bit again. I always just write it on my fingers so I don't forget. So this is the apparatus that we'll actually have. So here's a current source here. Current's going to flow through this thing. This is the positive sign, so actually conventional current's going to go this direction. Now if they flip these around, current's going to go the other direction. There's a magnet up here, so it's either going to be into the page or out of the page. And then down here, there's a force meter. So if the plunger here compresses, you'll see the dial go this way. If there is a repulsive force and this thing moves up, you'll see it go this direction. It's actually measuring in grams. We could figure out how much force that is from the weight, though. Remember, weight is equal to mg. So if this gives you the how much the scale is actually moving in grams, you can turn that into kilograms, multiply it by 9.8 meters per second squared to get the amount of force. More about that in just a minute. But that's the idea. Current's going to flow through here. There's a magnetic field. Moving current in a magnetic field, the wire is going to experience a force. So this thing will either move up or move down due to that force. Okay, copper wire going through this magnet, wood plate mounted on it. So that's what they're talking about here. The direction of the current is either going to be left or right. The magnetic field is either going to be into the page or out of the page. And then the force is either going to be up or down. It all depends on the right-hand rule. You've got to line those things up. Okay, so there's a series of videos below where you can choose the direction of B into the South Pole or out for the North Pole. So into the page is the South Pole, out of the page is the North. So remember what this notation is. So B into the page would be designated like this, like you're seeing the feather part of an arrow going away from you, and they're saying that that's the South Pole. And then B out of the page, like the arrow's coming out at you, they're telling you that's the North Pole of the magnet. Okay, good. So with that in mind, current left to right, we can play the video and determine the direction of the force by observing the motion. So once the person hooks these leads up, current's going to flow, and you're going to see this plate either go up or you're going to see it go down. So right now, the magnetic field is into the page, and the current is moving to the right. So when they tell you to, you can change that around. Let me make the screen a little bit bigger here. You can see that okay. And I can play this, and I can step through it if I want to. Maybe I'll do that to begin with. And the reason they don't let this play for a long time, you remember from the current chapter, current flowing through a wire, the wires are going to heat up. You could melt these wires really quickly if you just let the current keep flowing. Okay, so here's the positive side of this battery. So current is going to flow to the right here. And the magnetic field, this says the South Pole, so the south means into the page. So magnetic field's into the page, the current is moving to the right. From the right-hand rule, you could actually predict which direction it's going to go. Line those things up. So put your pointer finger in the direction of the current, and put your middle finger in the direction of the magnetic field again being into the page, and then you can see which way the force is going to be. So before you even do this, you could predict that, and then we can play it and see what happens. So the direction of the force is either going to be up or down. Okay, I'm advancing it frame by frame here. Oh, you see it move up. So the direction of the force is up. And then you can figure out how much the force is. So if you notice it was here on the 0, this is 10 grams, 20, 30, 40, 50, 60, 70, 80, 90, 100, and maybe about 108 or something grams. So that would be 0.108 kilograms. Multiply that by 9.8. That will give you the amount of force. The scale is just calibrated in grams instead of in newtons. Okay, good. So that's the idea here. We see that the current is flowing to the right. The magnetic field is into the page. Line up the fingers the way that you have to, and you can figure out the direction of the force, and the force was actually up in this one. Okay, excellent. So then you can answer each of these questions. Which of the following right-hand positions reflect the scenario of magnetic field into the page and current to the right? Okay, so, again, line these things up. And if it helps, do what I do. Just write them on your fingers, current, pointer finger, magnetic field, middle finger, and then force on your thumb. So the current was to the right. I think you're seeing a mirror image of me, so it's hard to do. It's flipped around from me to you. You're in a different perspective. Just line those things up, and you'll see which way the force has to be. Okay, and then you can pick it here. All right, excellent. And then which video matches this configuration? So same thing. What is this actually telling you? Well, line these things up. So pointer finger is where the current is going. So the current is going to the left. Magnetic field in this picture is coming out at you. And then this would tell you the direction of the force. So current to the left, magnetic field out at you. Let's just try it and see if it works. This is kind of a free one for you. All right, great, excellent. You like to see the green check mark there? So that's how you do it. You line everything up. There's a few different scenarios here. Same thing here, which is the direction of the force on the wire. So remember, the force is wherever your thumb is pointing, so you can see which way that your thumb is pointing there. Okay, test your ability to apply the right-hand rule. So same idea here. There are 6 different trials depicted in the videos below. Answer the questions following the video as they pertain to each trial. And again, note you only have 1 attempt for each question, just like before. Okay, so same thing here. Video question 1. What is the direction of the current through the wire as it passes by the magnet? Okay, so I don't want to give too much away. You can answer those. Which face of the magnet is facing out? So again, you can take a look at the picture there. These all go with this video. Okay. Okay, so this video question 1 goes with this video. The next one, you have to switch it over to question 2, right? So you can change that by hitting change, and then you can select question 2. I'm just going to do cancel here. So maybe I wasn't clear on this first one. What is the direction of the current? You can't tell by looking at the battery. Once they hook this thing up, you know that the magnetic field here, it's the south pole of the magnet, so the magnetic field is into the page. Once they hook it up, you'll know the direction of the force, so you'll know 2 things. The direction of the magnetic field, in this case, into the page. Once you play the video, you can see the direction of the force. The only thing that you don't know is the direction of the current. So when you line those things up, line up B and line up F, wherever the pointer finger is left, wherever the pointer finger remains, that's the direction of the current. Okay, so line up B and line up F, and then wherever your pointer finger is at that point, that's the direction of the current. And then switch it to video 2, answer the question for video 2. Same idea. You'll know a few things. You'll have enough information to solve for those. Okay, so this all deals with the right-hand rule. Okay, excellent. And then the magnetic force apparatus here. This is the next section. Same idea. There's going to be a current flowing through here. The scale down here is calibrated in grams. So you'll have to convert whatever it is in grams to kilograms, multiply it by 9.8. That will give you the amount of force in newtons. Okay, so each of these, like from here to here, is 10, another 10, another 10. So each of these small marks is 2 grams. It talks about that in the lab as well. Okay, very good. So in the video below, select the magnetic field pointing in, the current to the left, and then answer the questions. So same thing, you can change things around here. Whoops. This is kind of getting us started on reading this. That's what this section's all about. What's the maximum scale reading? So you again get it in grams. And then it might seem like they're asking the same question here, but this question here deals with how much is the force in newtons. So change grams to kilograms, and then multiply it by 9.8. And then you can show your work here, or if you want to upload a picture, you can also do that here. Okay, and then the last part is force versus current. And this section, you're just going to be using magnet A the whole time. Okay, it says please select only one answer. We're only using magnet A. This is the magnetic field strength, 0.1337 Teslas. So click this, submit answer. That's what we're using. We're not going to use magnet B, magnet C, or magnet D at all. Just magnet A. Okay. So in this part, we're going to know how much current is supplied, and we're going to see the corresponding force. And again, this force is going to be in grams. You'll have to turn it to kilograms, multiply it by 9.8. Okay. It's the same thing. You can play this and see what it looks like. Select the trial for your magnet A in the video. It's already preloaded on magnet A, so you don't have to do anything. But if you happen to play around with it, make sure you go back to magnet A when you make the graph here. And these are both ammeters, so this is measuring current. You can, this is the power supply. This is an actual ammeter here. Okay, so this one is probably a better one to read it at because you can see it a little more clearly. Okay, there's more lines here, so there's more precision with this one than there is with that one. This one just so happens to have a meter here because it's a power supply. They should basically be the same thing, but you can see it better on the one on the right-hand side of the screen. Okay, so that's going to give you the amount of current. Actually, let me just kind of step through here so you can see what it looks like. So they're going to turn it on, and they're going to step through this. They're going to increase the amount of current. It starts at 0. And they've turned it up to, it looks like, 5 amps. And then you could read how much force there is. There might have been one before that, actually, that I missed. Let me go back and see. So around, I don't know, maybe. Okay, so that's, nothing's going on because you want to take this data like you were in the actual lab. So whatever that is, your eyes are probably better than mine. Looks like there's a certain amount of current here and a certain amount of force. So there's going to be a data table. You can enter that number in. So it's good to step through this. You can't do it all in one shot. And then now they're going to turn it up again. Looks like we got 5 amps, and then you can see how much this reading is. Again, that's in grams. Convert to kilograms, multiplied by 9.8. There's another data point. And they're increasing it again. Okay, it looks like still going. And then you know, watch the person's hand and watch this. Actually, that's what I should do too. Okay, it looks like that maybe that's a reading, and this is how much force. So you want to go through. You don't want to just get 2 readings. One, you know, a current corresponding force, a current a corresponding force. You should be able to get 5 or 6 of those, you know, to build a nice data table. Looks like we have 10 amps, and then here's the amount of force. You get the idea. So go through and get several data points. And you can put them in this table here. Now, it looks like it's already kind of set up for you. So 0, 2.5, 5. So here's the amount of currents. Watch the video, and then you know what you want to name this force. The units would be however you want to do it. Maybe you have a column with grams. Maybe you want to add another column. You can do that. Insert column to the right. So maybe you want to have a column in grams. You can do another column in kilograms, and then you could do another column in newtons. However you want to do that. And then you can make a nice graph here. So we did graphs in a previous lab. So on the vertical axis here, you could select whatever you want to put there, and you can call it whatever you want to. And if you click here, horizontal axis, whoops, you can click whatever you want to put there. So just click on here, whatever you want to put on the horizontal axis. In just a minute, I'll tell you what we're going to be graphing and what's the reason for that. And then you could put the here, it's going to be a linear graph, so you can put a line graph there. Okay, so what are we graphing and why are we doing this? Let's take a look at that. So ultimately, the graph is going to be something like this. Here, vertical axis force, and we're going to have that in newtons. And on the other axis, we're going to have the amount of current, and it's measured in amps. So you should get a graph that looks something like this. So remember what a graph is. It's like y is equal to mx plus b. In this example, b is just going to be equal to 0. So we're plotting f on the y-axis, and we're plotting I on the horizontal axis. And here's the formula that we have. F is equal to I L B. Okay, let me rewrite it like this. F is equal to LB times I. So F plays the role of Y, and I plays the role of X. So whatever comes in front of the X variable is the slope. So this is the slope. Slope is equal to L times B. So what we're trying to figure out is the length of this thing. Okay, so when you put the equation of the line on the graph, it'll give you the slope. You don't have to calculate the slope by hand. The equation of the line will be there for you. The slope is equal to L times B. So if you take the slope and you divide it by B, and remember B is given, it's we're using magnet A. It tells you what the magnetic field strength is. This will be the length. That's the length of the wire that's actually in the magnetic field. Okay, so you make a nice force versus current graph and get the slope, and then from the slope you can figure out what L is. Okay, let's go back to it. Okay, so again, you make your nice graph, and you can figure out the length just the way I just told you. And let's see what it says here. You now use your graph to calculate the length of the wire. Briefly explain how you would do this. Okay, good. We did that from the slope. Calculate the percent difference between this value and the length that you calculated. So you can actually, measure the length of this with the length tool. And how do you do that? So in the video, there's a toolbox here. And you could use the ruler, and you could measure the length of the wire that's in the magnetic field. So that would be this part from here over to here. You can take this and line it up to measure the length of this thing. A little bit of estimating here because looks like it's not quite all the way there. But that's the part of the magnet that's in the magnetic field. Well, this magnetic field is just not here. Probably some of it goes to this part, some of it goes to that part. So that's a systematic error built into the lab. I think it asks you to talk a little bit about uncertainties. So you're measuring the length. I mean, which length should you actually measure? Should it be from here to here? I would say measure from here to here, but then really this part of the wire and this part of the wire, experiences some of the magnetic field as well. So we're doing a little bit of estimating. Okay, very good. Well, if you have any questions, let me know. It's kind of a fun lab. It's one that it's hard to do actually in person. This is one that works better when you're online like this. Okay, shoot me an email if you have any questions, and I'll talk to you soon. Bye-bye.